In this video, we're going to explore Le Chatelier's principle, which helps us understand how the position of equilibrium is affected during a reversible chemical reaction. Specifically, we will look at how changes in temperature, pressure, and concentration influence this equilibrium. From our previous understanding, the position of equilibrium describes the relative amounts of reactant particles and product particles in a system at equilibrium. If there are more reactants than products, we say that the equilibrium lies to the left. On the other hand, if there are more products than reactants, the equilibrium is said to lie to the right. Le Chatelier's principle states that if we change the conditions of a system at equilibrium, the position of equilibrium will shift in such a way as to oppose that change. In other words, the system tries to counteract or undo whatever change we introduce. This principle is extremely useful because it allows us to predict what will happen if we alter the environment in which the reaction is occurring. To see this principle in action, let's consider the Haber process, which is used for the industrial production of ammonia from nitrogen and hydrogen. The balanced equation is N2 plus 3H2, 2NH3. Now, assume that this reaction is occurring in a completely sealed system, which is necessary for equilibrium to be achieved. The forward reaction, which forms ammonia, releases energy, as shown by its enthalpy change of minus 92 kilojoules per mole. Because this value is negative, we know the forward reaction is exothermic, meaning it gives out heat to the surroundings. Consequently, the backward reaction, which breaks ammonia back down into nitrogen and hydrogen, is endothermic, as it must absorb heat. Let's say the system is initially at equilibrium, with balanced rates of the forward and backward reactions. If we now decrease the temperature of the system, the equilibrium will try to increase the temperature again. Since the forward reaction is exothermic and releases heat, the equilibrium will shift to the right to produce more heat. As a result, more ammonia will be formed and fewer nitrogen and hydrogen molecules will remain. Alternatively, if we increase the temperature, the system will try to cool itself down by favoring the endothermic reaction. In this case, that's the backward reaction which absorbs heat. So the equilibrium will shift to the left, leading to more nitrogen and hydrogen and less ammonia. Le Chatelier's principle also applies to pressure in a closed system, particularly for reactions involving gases. Pressure is essentially a measure of how many gas particles are present in a given volume. If we increase the pressure, the equilibrium will shift to the side with fewer gas molecules, because this reduces the overall pressure. Looking at our ammonia reaction again, we have 4 molecules of gas on the left side, 1 nitrogen and 3 hydrogen, and only 2 molecules of ammonia on the right. So, an increase in pressure causes the equilibrium to shift to the right, favoring ammonia production. Conversely, if we decrease the pressure, the equilibrium will shift to the left to produce more gas molecules and restore the pressure. Finally, let's consider changes in concentration. Suppose we increase the concentration of nitrogen by adding more nitrogen gas to our sealed system. According to Le Chatelier's principle, the equilibrium will shift to the right, where nitrogen is being consumed, to reduce the effect of the increase. This results in the formation of more ammonia. On the other hand, if we were to remove some ammonia from the system, reducing its concentration, the equilibrium would again shift to the right to replace the lost ammonia. Essentially, the system is always trying to maintain balance by countering the changes we make. To summarize, Le Chatelier's principle tells us that a reversible reaction at equilibrium will adjust its position to oppose any change in conditions. A decrease in temperature favors the exothermic direction. An increase in temperature favors the endothermic direction. An increase in pressure causes the equilibrium to shift to the side with fewer gas molecules, while a decrease in pressure does the opposite. Changing the concentration of a reactant or product causes the system to shift in a way that consumes the added substance or replaces the removed one. And that wraps up our explanation of Le Chatelier's principle. If you found this helpful, feel free to leave a comment and be sure to subscribe for more educational content. We'll see you in the next video.